Okay, we're going to continue on the theme of trying to avoid bias in AI. Sharon King, who's Chief of the Division of Vascular Surgery at the VA in Loma Linda, is going to talk to us a little bit about cognitive bias in AI, how computer vision can be gender biased. Sharon.
Good morning, I think it's still. I want to thank the foundation, Dr. Conti and Ms. Bjork, for creating such an amazing program, because somehow magically, everything that has been discussed and was just discussed is going to lead into actually this talk. My research and my focus is specifically on computer vision. So a lot of this talk is based off of the data and the philosophical algorithms for that. These are my disclosures. This is my funding. And AI is not new, right? We know it's been used in the corporate world, and stock market predictions, atmospheric models, blockchain technology has been used for over 2 decades. What we have that is new is that AI is finally permeating into medicine. And I think it goes into a lot of discussions what we've had now. What is responsible AI that is patient-oriented, patient-driven, and how is the translational efficiency of that going to be safely guarded, right? Even either through oversight administration. We have a lot of what we call big data, and we can start with a simplistic model, which is EMR, clinical data registries, health information programs, but in the genetic world, we've had it all along, right? Gene sequencing, DNAs, different variations of genomic manipulations. We've had it for a long time, and AI is finally gonna be able to flex its power, because the potential of the AI is its ability to compute large and heterogeneous imaging and biomarker data sets, and to identify patterns, if their relationships are complex and non-linear. AI doesn't tire, and AI is not confined by the linear outcomes of how we like to think about data, how we like to think about outcomes. So we can merge different forms of data sets and have it in a responsible, puristic way. The potential is there, and the potential is enormous. Now, we talked a lot about disparities, right? So some of the stuff that's popped up, healthcare disparities, algorithmic fairness. We talk about poor, undeserved studies, because AI has a way to take small, marginalized populations and create systems that we can project algorithms and outcomes. But it comes with a cost, and we talked about that in the last couple of talks. And this is just a quick screenshot of stuff that people talked about. Bias, bias, bias. Is it against race? Is it against gender? And to what Dr. Ross just mentioned, AI recognition of patient race and medical imaging modeling study. In this study on chest x-rays, even though there were no race-specific identifiers, they were able to figure out what the race was. Additional studies in this topic in computer vision specifically looked at intentional disintegration of imaging and found that even with the image destroyed, disintegrated, fragmented, they can still identify race. So that leads to the question, what is AI computer vision seeing? Sidebar. When we talk about vision, it is actually an interpretation, right? We rarely actually acquire specific individual constructs. We actually take what we know is an image recognition, and we do it by rote and experience, and when we see something, we actually interpret it and understand it. Clearly, the computer vision is doing something different. So some goals of this talk is, 1, challenging our idea of what data is. We're good at clinical data, but when we try to marry the two, so let's say in translational work, we need to understand what AI data is. And in my context, computer vision data. What is the computer seeing? And 2, one of the other goals is just one of my personal passions is marrying the lingo that we use to talk about this, right? Some of the talk I'll have today is described and very detailed, but when we reduce it into how I write a grant or manuscript, it's reduced to one single line, which is the AI talk. And I think that is where the disintegration between clinicians and computer scientists and new technology can become a quagmire of confusion, because if we don't understand how they talk, we're gonna overly interpret and draw conclusions perhaps that shouldn't be drawn in the first place. The other thing we're gonna do is we're gonna take virtual trips back into my lab as a case study to really focus on the points I'm talking about. I presented this several years ago, so those of you who've heard it, just take a quick nap or something. Like I said, I'm really into computer vision, and how I like to work on computer vision is developing convolutional neural networks. Essentially, my lab is trying to replicate the visual cortex, and in my particular subject matter, we like to use the aortic aneurysm as the subject of study, right? We like to use CT scans because of high volume, low variability, good efficient acquisition, and pretty much uniform ability of current helical CT scanners to acquire data information. So this is just a pictorial that I'm not asking the computer to memorize that aneurysm, that intramural thrombus. I need the computer to understand the concept of aneurysm. So that is the premise and goal, hopes, dreams of the lab that we're working on. So we developed a VGG16 model. It's a high flexibility model. We boosted the performance of the model by different hyperparameters and augmentation methods. Sounds a lot of gooply-gook, right? We're gonna go into that in detail so you know exactly what I did. And since I've now designated all of you guys as my co-Is, I'm gonna show you what I did wrong and have you guys also help me figure out how I can fix it. Long and short, we put in 13,000 images and actually had this algorithm be able to identify to an AUC of 0.99% the presence of an aneurysm, unsupervised. So this is automatic, unsupervised. It goes in, it knows what it's doing, 0.99, great. We then went in and took a deep dive into, well, did it really understand how well it could do based on size? Did it get confused if there's adjacent aneurysm? Did it get confused with thrombus? Long and short of the story is no, the algorithm did really well. So I was like, great, 13,000 images, institutional model, let's expand it out, let's see if we can go ahead and apply this algorithm to other institutions. And then I thought about that thing about the chest x-rays, and I said, well, you know what? Let's take a deep dive in. Let's, in this particular case, it's a university model, so let's look at females. Let's see if we pull that population out, if this algorithm can still do its job. And unfortunately, it couldn't. So we created 6 alternate training pathways and found that when we trained it on females to look at outcomes, it could only reach an 87.7% specificity and could not reach the 99, right? And so we did all sorts of things. We realized there was a class imbalance, less than 50% of the population was female. We increased the numbers. We did some augmentation techniques. What does that mean, right? It really just means I try to minimize the disparity between the two numbers just on algorithm alone. And that led me into a whole different line of investigation, right? Which is bias and fairness in algorithms. Am I picking up a true difference, or is there something wrong in my model? So just taking another step back, we'll take many steps back, algorithm fairness is a real thing. It is an emergent field of machine learning. It tries to mitigate the difference in modeling outcomes between social gender groups, really anything that's a minority outlier group. We know those groups have smaller numbers, smaller representation, and they actually don't have equal ways of representation within a data model set, right? If we take female aneurysms, for example, we know that overall, anatomically, they have smaller vessels, they have worse access, they present to healthcare providers later, they have more advanced disease. We know that they're offered intervention less and more likely to end up on some sort of palliative intervention. We've replicated that in the oncology model, we've replicated that in the thoracic aneurysm model. We know that there's a difference. So an ideal model, we've talked about it in different forms in other speakers, is a blinded AI model, right? It should be blinded to sex, race, gender diversity, et cetera, et cetera, et cetera. But the challenge is how to create a model that truly spits out an outcome of what you're trying to study versus a useless model. Because if we take all that out and we try to study disparities that way, then it becomes a useless model that is not useful for that data set of that population that you're using. So where is that balance? And I think Dr. Sakuja had a really nice thing, right? Where is bias and where is the outcome, right? And I think we don't know where that line is. So I'm only gonna talk in the context of computer vision. In a larger scale, this problem within the wheel, from data handling to its entire algorithm to evaluation, can happen at every part of AI. It can happen at the ML level, it can happen at the deep learning level, which is where my lab lives a little bit right now. So we're gonna use this wheel to actually pick apart what I did, pick up some new terminology, and talk about data, and specifically data in the context of computer vision. And reality is we're gonna only handle the 2 major fundamental starts of that wheel, because if your data is terrible and sucky, I'll put it this way, the rest of the algorithm decision-making doesn't matter. Garbage in, garbage out. So the rest of the wheel doesn't even matter, and the first 2 spokes aren't handled. So I'm not gonna itemize all this. This is way too much stuff, and I don't expect anyone to memorize. I'm just gonna fundamentally list out the types of data. We've talked about natural language processing, But we're also going to talk about what is structured data, unstructured data. We have numeric data, you have categorical data. My world lives in imaging data, which is just number 3. You have text data, right? When people are trying to troll the millions of, let's say, documents and whatever they're finding, or dictation reports, or whatever, that's like text data. You have time series data, things that follow a chronological sense as a prediction model. You have audio data, right? I help supervise an audio group that actually tries to mimic the function of the cochlear system. And the way they try to synthesize sound to try to replicate and look at margins of error is super complex. Not my field, so that's all I'm gonna say. But it is amazing how different we think of data. And we have sensory data, structured data, et cetera, et cetera. But all these different forms of data has a different way of data handling. And this was alluded to by some of the speakers already, right? In the large nutshell, you have raw data, and you have processed data. Oops, stepped away from the microphone a little bit. Raw data essentially means it can be qualitative or quantitative, but the large nutshell of it is it's not cleaned and it's not processed. Raw data is extremely time-consuming to evaluate. It has not been categorically classified. It has not been clustered into ideas of outcomes, which is how we like to think about data. If you think about how we collect data for registries, right? Anything, VQI, NISQIP, TQIP, whatever, clinical registries. We clean that data up. Very rarely are we just inputting numbers. We have a data scientist, we have a statistician, we partition it out. But that is processed data, and it's much, much easier to think about it because it is goal and linear oriented to what we want to see. There are pros and cons to both types of data. And in computer vision world, raw data is exquisitely important because you can imagine, well, some people question, how can there be processed data in imaging, right? Like it should just always be raw data. So we're gonna take a quick trip down the road of computer vision. So I like to use the humble kidney as an example. This is an ode to Dr. Sakuja, who's sitting right here, didn't realize it. When we look at this, we are looking at different shades of gray, different variations of hyperechoic, hypoechogenicity. We make some judgment about the size, the contours, if it looks shriveled, if it looks like it's a CKD, impending dialysis patient, things like that, right? We think about all these things, and that's an interpretation. The computer doesn't see that. There makes no judgment on everything I just said, which is what every clinician in this room just stared at that kidney ultrasound and thought about. What it does, instead of seeing shades of gray, the computer sees a matrix of numbers representing pixel brightness. It is then categorized into, from a medical image, it is transformed, given a statistical probability of what it is, and eventually cones out of the detailness, and gives it and makes little pockets of statistical probability of what that kidney is. And as it keeps doing that, that's what computer vision does. There is no judgment and no interpretation of this. This is purely on data acquisition and translation of pixelation into a statistical probability, right? That is computer vision. And this is why raw data for us is so important and why processed data becomes a problem. So CT scans the same way. This is not just an ultrasound thing, right? This is a CT scan. So in a convolutional neural network, we create internal representations by multiple layers of thousands and hundreds of thousands of visual features by stacking the layers, like I talked about, just the first picture that I showed up. And this operation detects features of interest. In my case, was an aneurysm. And as you train the data set with good data, unprocessed raw data, it understands how to create consistent representative pockets of statistical probability, right? That's how you get the machine to identify things. So CT scans, raw as it gets, right? And I think there's a lot of great papers being written about computer vision, and some stuff that I'm just like, they probably didn't understand the principles of computer vision. So we're gonna start with the basics. On the far left, you have a low dose initial scan. In the middle, you have the raw unprocessed scan. And in the far right, for any radiologists in the room, please pipe in, is the cleaned up version. If you think about the helical CT and how data acquisition is maintained, it is not one complete revolution of that one slice. You lose about 25% of imaging of that slice that you start with because you've moved on to the next slice, right? So what it does in the post-processing image, which is the clean, pretty version we all like to see, is the general volume averaging of those slices that represent that slice as the helical CT turns. The missing data points from the middle image to the far right is filled in based on variations of volume averaging probabilities that that pixelation happened at that point. It seems so easy for us as humans because, well, yeah, if I'm missing a dot in the middle of the kidney, of course it's going to be lighted up, right? But the computer has to generate that. Now, I like to think that at some point there's a rabbit hole to this, because clearly I am not measuring photon decay in amount as it goes through CT scanner, right? That's as raw as it gets. But I like to think of this as the raw basis of a CT scan. So when I read studies that look at CNN prediction models off of recon studies, this is an accumulated amount of error based on estimation from the original axials. Then when I read studies that talk about prediction models off of 3D recons, that is estimations of error on the log factor 2 scale. In our global view, it doesn't matter, because we interpret these things on total, en masse, because we understand the concept. Don't get confused, this is not the same kidney going through. But anyway, but to a computer vision, this error to scale becomes a logarithmic error that expands on. So think back to the female with the aneurysm. We know females have differences in delta and change as, let's say, the helical scanner goes through, right? We know they have overall smaller vessels, more calcified vessels. They are presenting later. There are biologic issues with women that demonstrate now that there is higher errors of aneurysm degradation, expansion, especially when they meet postmenopause. All that stuff, even on a computer vision level, you can see be fundamentally different than if it was a male aneurysm that I'm scanning, right? So this is just a very, very, some people might say minute point in computer vision world, but I don't think it's minute, because this is on one patient. I'm already pointing out the error to scale, magnified it by 13,000 images that I just talked to you about in my one study, times 6 medical centers, times large geographical populations. That error should normalize across the board if everyone's getting it, but not if we don't have the large numbers to scale, right? And which is what we don't have right now. So we do have to pay attention to this and take it into account when we're building models. So we talked a little bit about data handling, and that unfortunately is not where we end, because parts of augmentation and data interpretation becomes a problem too. So taking a trip back to the architecture I talked about, one of the things that we noticed was, and I mentioned it already, was the class imbalance, right? We built the model as a heterogeneous conglomerate, but if you've got basically, 2/3 of the model being male and only 1/3 being female, any model in that context is going to normalize to the larger population. It's simply just the way it's going to be based on computer vision. Remember, it's statistical probability of identification of that kernel, right, in computer vision. So we actually had to go back and see what we did, and what we actually did at that time was we did something called ROSE, which is random oversampling of the example. So the one thing that we like to do in deep learning and ML is we create synthetic data based on just the normalization of the undersampled population. And we try to minimize the class imbalance, right? We try to match the cohort numbers, if you want to think of it in a clinical research way. This happens a lot, but no one says, oh, we created synthetic data to minimize the class imbalance and match the cohorts. What they're going to write is in their methodology, we use the random oversampling example rows to this algorithm right here to minimize the class imbalance. But when you read that in the paper, that's exactly what the computer vision people did. They created synthetic data. So this is for binary classification, for example. In rare classes, let's say low frequency disease models, in this case, a lower population model, it's a synthetic data. Usually it's balanced, and it's based off of the sample data that accumulated through the original data set, right? So this is really important because no one in their papers writes that we synthesize data. They're just gonna write that and expect you to understand and accept it that that's true. But what's the problem with that? Now, synthetic data has a role, and I just told you, synthetic data is modeled data off of real world data to mimic the probability and variance of its representation. And the idea is always to equalize the group that's not being well represented, right? So they can be the outliers, the low frequency disease models, in my particular case, the female aneurysm. So it is powered by deep generative algorithms. Thank you for Dr. Patel, who talked about that, right? They use data samples as training data, and they learn the correlations, statistical probabilities, and data structure. And ideally, when it is trained on that data set, it can create new data that mimics, again, the representation of the original data. It is a better way to anonymize, because for very sensitive data, you may not have a lot of it, you can create synthetic data to run the algorithm without exposing whatever sensitive material. You can actually stress test the model. Sometimes outliers that you're trying to test are so represented so little, you don't have a way to test the efficiency and outcome and output of that algorithm, right? So you have to create synthetic data, just so even you can test the original algorithm. And then you can fix the data imbalance, which is what I did, right? So the question is, if I actually had an error base out of the acquisition of the data, then I use that data and create a synthetic data to balance my data set, if I just created more errors. And is that what led to the poor performance of my model, right? I don't know. So that's one thing that I'm looking into to see if that original data representation was even good enough for me to use the rows over sampling data. So this is something I think someone else mentioned, is synthetic data has all those great things, but it can perpetuate and augment the bias of the original data. And this is one of those things where it is very hard to figure out, because what is the main goal of most people that design algorithms? It is to optimize the performance of that system. The goals are very different in AI world compared to the goals in clinical world, which is not to optimize the performance of the system, but to optimize a model that represents the patient clinical question that you're trying to answer, right? So when I talk about these things, I kept it in the back of my head. Am I really doing the work right now to figure out the gender imbalance and the gender changes in outcome-output models? No. What I'm really doing is trying to optimize the algorithm and the code that I've written for this. And like I put in the parentheses and, well, I guess italics and bold, efforts in using augmentation systems to class imbalance and things like that, it, in a way, removes the real-world data model just to result in an output that's focused solely as model performance. I actually wrote that in a paper, right? Because I realized this is a problem. The question for my all co-Is out there, congratulations, how do I solve this? Do I go and just get more people? Yeah, we're doing that now in the lab. Literally enrolling more centers, grabbing the data, getting the CT scans, and then realizing even doing that, how poorly access to care is to the female population, especially in the aneurysm world. And I think aneurysm is one of those things where it's kind of dime a dozen, right? Everyone gets CT scans for diverticulitis or whatever thing that comes in through the ED. We should pick it up. We should pick it up equally. Why females get hurt just as much as males get hurt, et cetera, et cetera. We should be able to do this, but we still cannot get the numbers. Different problem, different question, but I just want to let you know this is what's going on in my head. One other thing that comes into when I was trying to create this system to be better, right? Again, is it a population system or is it an algorithm thing in my computer vision, is the augmentation. Now, what does augmentation mean? It's a word that you hear all the time in AI world. No one really knows what that means. So here is the augmentation part of it. As I mentioned in my paper multiple times, it's how I boosted the performance of the VG16 model. Gobbledygook. It's like Klingon every time I say it, right? No one really knows how to respond to me. Is it positive? Is it negative? Are they booing me? So augmentation is a technique used in AI to artificially increase the size and the variety of the data set by making small changes to the existing data set. In this particular example, we're going to use butterflies. So here's a monarch. When I only have 2 real monarchs of that particular representation, I have to find a way to represent all the monarchs that may exist. This is not about numbers. This is not about the class imbalance and I'm using rows over sampling to create synthetic data. This is me trying to create every representation of that possible monarch and its variability to represent that population. So that's what I did as well. Not only did I boost the numbers of the female in that group, I also did the augmentation. And how does that all come together? It comes together in this little pictorial graph of cats and dogs, right? We have the class imbalance, right, of males and females in the visual study. We can't oversample it because that's not representative of the distribution of that disease pattern as it was being collected. You can't undersample it to normalize it because that's also not representative of the distribution and incidence of that disease an aneurysm in the visual study. So not only did we create more synthetic data, but we also did data augmentation. So it can completely represent the variability of how that CT of the aneurysm comes across, right? We did all that to try to fix this. And guess what, ladies and gentlemen? I didn't fix it. I could not synthetically even manipulate my model to make it as good as my male model. So it's deeper, right? We talked about raw and processed data. What no one has asked me in an alarming urgency is, how did I keep the confidentiality of these patients sacred, right? We know DICOM images embed a lot of data that we don't see. We only see what we see, but the computer sees more. And I knew that, so from the get-go, I programmed an anonymizer in my core system. So every CT that comes through gets scrubbed of all identifiers inside, right? Maybe I degraded data in that process. In my effort to anonymize my patients and protect their identity and follow HIPAA regulations, I basically degraded that CT, even as it was coming into my core system, right? So I started thinking about all this, right? Because there's larger questions to be had. If this is really all the errors in that spoke that I have a problem with, how am I gonna fix this short of literally just finding every woman on earth and like ask them to give a CT scan for diverticulitis, apparently, right? So these are the things going through my head, and I hope you guys have enjoyed some virtual trips back to my lab, and this is the system we have. We are currently enrolling lots and lots more women, engaging more medical centers, because I need my overall raw data set to be bigger. Now, I know the male cohort is doing fine, right? And I need the female cohort to be bigger. Does that mean I will not be oversampling, creating synthetic data, maybe augmentation? No, because I'm never gonna be able to balance equally between the two class imbalances. That's simply not the demographics of the representation. I am incorporating many more variables in, not only to the male line of investigation, but also into the female line of investigation, because what does AI do? It incorporates large data and creates nonlinear connections. So this is a global sampling, well, pictorial of what we're trying to do, whether I'm successful or not, different issue, right? We talked about the AAA 3D reconstructions and its errors in that, but I think there is value to understanding how is geometric conformation can actually add to it. You are correct, in my actual modeling, this is a thoracic saccular aneurysm, and that's because on the initial get-go, those aneurysms are easier to model than the infrarenal model. I don't have any branches, I don't have actually, neck sizes. I can actually create a synthetic model to measure geometric influences into my algorithm. So we're programming that in right now. And then within that construct, the hemodynamic properties, so the resistance, the flow, the rate per systole and oscillatory cycles, we are incorporating a hemodynamic line into my model as well. Because if we can understand also the behavior of these aneurysms, I think that's one leg above than just simplistic computer vision at a static level, all right? So this has turned into an incredibly rabbit hole delving thing. We're using finite element analysis. We are violating the laws of physics because the compliance in the wall has been negated to one integer, so I'm not taking that in account right now. And we're building multiple variabilities based on conformation, fusiform models, intramural thrombus, and actually, branches that come off and things like that, right? And I know, I feel it in my bones, this will be a huge game changer between men and women, right? Between the hormone changes, between the compliance, between the degree of the vessel size and disease, this will be different. And I just have to be able to computationally figure out an algorithm that properly represents these models. And we love clinical data. And there's like plethora of hundreds of clinical data points. Currently I have 64 implemented into my model, but there's more I can collect, right? Beyond medication, beyond just lipid, beyond just, INR or something like that, right? And one of the things that has been an issue in AI world is, how do you take basically non-translatable data points and measure it so that they are comparable to each other, right? We talked about this model that we built for computer vision. So I took that model, stuck it in the right-hand corner, and built an ensemble model. So the weight of a computer vision data can be equalized to a categorical model, let's say like a creatinine, something like that, right? Because how would you even, how do you equate that. We like to write about it in clinical papers as like it's associated with. We have known that in this large retrospective study of 5 billion people, we see that this INR is associated with this type of whatever SAC increase. But in reality, that's not a comparable thing. That's like comparing apples to like a spaceship or something, not even an orange. It's not even the same category. And that's where deep learning comes in. This is a hybrid-based model, partially supervised, partially deep learning. Ensemble, meaning multiple streams of model algorithms that are built into a central line of spitting an output that is interpretable. In my mind, this is one way that we can start really investigating the differences in outcomes, not just from diagnosis and imaging recognition, but even aortic remodeling between male and female, maybe post-repair, or even understanding the behavior of how these aneurysms degenerate, leading to different rates of, let's say, rupture, focal points of rupture. In that 3D model, if I can figure out where the point of lowest, highest wall weakness, then I have an idea, of how these things will eventually rupture, and I can give you a guesstimate. Hey, you want to go on a cruise? No problem. I'll see you in 7 years, because that's when things will really start getting exciting for you, so make an appointment with me at that time. I would love to say that to someone so that we can be more precise, we can customize the care for these patients. Literally, someone just told me last night in Uber, how many people in this world? 8 billion? Are we really gonna do surveillances every year for 8 roughly billion people? That is not a sustainable model, right? So we gotta find a way for AI to work. This is my lab. I can't have done any of this without all these people. I cannot have done this without you guys for giving me the space to talk about my dreams and fantasies and this mythical novel I'm writing right now, because this is not a space that is necessarily present in the clinical meetings. It's not a space that's present necessarily in the basic science meetings. So this has been a perfect opportunity for me to tell you what my lab is doing. So thank you so much.
One where I was like, can you get enough data to answer a question? And you were talking about how raw data might help you. Have you, in the coronary world, people have started to do the same thing with ensemble data, with the direct angiographic pixelar data? One of the things that I've seen some people starting to do is something called more data in one patient, or smaller numbers of patients from many different areas. So not just the raw data from a coronary angiogram, but physiologic data, and then follow-up data. I'll call it, quote unquote, the digital twin movement, to say I'm building a digital twin for this person, where the computer's running over here, telling me when this person's going to get sick. When they come in, we check their blood pressure, their heart failure metrics, and oh my gosh, look, they don't.
Yeah.
The example in the cardiovascular field is we have these implantables. So somebody's walking around continuously getting their PA pressure measured in heart failure. Now this computer's over here predicting what will their PA pressure be. Have you thought for your aneurysm model, even simple measures like blood pressure or invasive measures, if you had a lot of them in patients, does that help you?
So that's one. So in the the hemodynamic line, the second one where I'm talking about the flow models, we are measuring that at the time we acquire that flow data, because I think that's going to be one of the variables that are going to be connected. Obviously, we have collected the clinical data like that within the clinical line too. Harder to interpret, because that day in the clinic, they forgot to take their blood pressure medication. Who knows what that means, right? So we're collecting in real time as we build the model. We have some very, very, very primitive live model patients that we're collecting the data from. And we're trying to match how well that matches with our synthetic model, because literally we're not going to be able to go to every, aortic case to try to measure this in live time. There has to be a sustainable way to build that line of the modeling too. At the reception last night, someone was telling me about their Oura ring, and I hadn't even thought about that. There you are. Because there's so many patient or individually based wearables now that there is that data there, right? Am I gonna contract with Oura? Maybe, I guess I'm writing them after this. But they have the Oura rings, they have those other monitoring things that people use for claudication, PAD observations, compliance measures. That's all there floating around untapped. And I think one of the great things about like AI, especially the ensemble deep modeling, is you never know which variable is going to be an issue, right? I work at Loma Linda, which is classically called a blue zone, like where people live like to a billion years old or whatever, and they never get sick. And then there's Okinawa. What is about these places? So we should also be collecting, and I've proposed this to my scientific team who just rolled their eyes at me, distance from the medical center, altitude, temperature, atmospheric pollution, all those things collected together. Now, who's going to do it? No idea. Depends who funds me. But yeah, that's all that data there. And I don't know in the end if we can get this into the thousands and tens of thousands where that modeling can all come up. We know there's associations with that with certain disease models. Carotid body tumors is the one that comes to mind, right? There's something about these things, right? And I think in the cardiology world, you guys are already light years ahead because you have stuff that people can use. I mean, I can't stick a Holter monitor in someone's abdomen. It's just not going to work. Hey, Matt.
I'm glad to see investigator-driven computer vision. I'm doing some of this myself. There's a lot of companies doing this too, and I've had 3 of my different partners where I work approached by a company that wants to give us a free trial and wants to ingest all our CT scan data. So how do we, as an institution, balance who gets access to that and how we prioritize? Because that same scan's got coronary calcium, it's got PAD information, it's got pancreas on there.
Yeah.
How do we prevent our patient from being attacked like a swarm of bees after their CT scan from a bajillion different people with a single organ, single diagnosis focus? Because I really could see this becoming a real can of worms, particularly in areas like PAD where maybe overtreatment is a big problem some places.
That's a great question, and you hit on one of my soapboxes. To all my industry sponsors in here, thank you so much for your generosity. So please take my next comments with a grain of just generosity. Someone in here said AI is the wild, wild west. Well, data is your new gold. Data is everything. I think for companies that come in that want to scour your PACS system for earlier notification of AAA, all that stuff, there is a role, but when you really think about what they do, what they're doing is coming to your system and acquiring data. When I think to what they say, I don't know how to validate what they do. If you have a false negative, your radiologist is going to catch that, right? But does that get back to the company? Probably not. I don't take their face page proposals as the true fact. So AI has a double entendre, like a double-edged sword, right? We in this room are academics or patient-focused physicians in the past who've always been driven by quality care, patient-centered outcomes. Companies, which have funding in the billions, right? NIH funding is in the millions, they have funding in the billions, are gonna far outstrip this pace faster than we as academics in our labs can grow this stuff. They don't have the same problems, but they have different incentives because they're all about algorithm and incentivization of money, of generating business, and they hide behind intellectual property. There's no way I can walk into one of those places and be like, I really need to see what's going on because I don't know what you're doing with our data. Is that data secure? Is it gonna be scrubbed? Because data is forever, right? I talked about this at FAM. Oversight for these people has been driven by monetary things from the institution. They think they're just gonna fire all the radiologists. They don't need them anymore. Early detection, maybe get rid of the paging system and throw the pagers out the door. It's incentivized by little things like that, right? They think it's going to increase throughput and processes. And when the C-suite, which are like non-vascular surgeons, think about this, it all makes sense. To me, it doesn't make sense. We're losing something really valuable. We're giving control over to somebody who doesn't have our same interests. They have billions where we only have millions. And our I guess, stake in this is bigger than theirs, right? Because they ultimately are going to affect the way we work and how we treat patients and how patients' trust in us may evolve. Right now, regulation is very reactionary. They see something go wrong, they clamp down. The federal government at the VA wants massive big brother oversight over everything, clamp down, report everything, and it's just because they don't really know how to look at this. I think each institution is very different. I think, again, even a rural hospital, limited vascular surgeon covering like 3 counties or something, maybe you have to do something like that for the safety of your patients, right? Maybe you have to implement a system that takes the middleman, which is what they're calling us these days, out of the picture. But I think for the university systems, large medical systems, I don't think we have to be in that boat. And I don't care what the C-suite says about cutting costs and improving processes and throughput, down, sizing radiology staff, and, I think we're always gonna have to be there because there's no way that we can really regulate those people coming in. So I would argue that data is kind of key, and I would be arguing the security and HIPAA issues with people that really promote these things. For anyone that works for those companies, so sorry. But this is a circle of trust, so there we go. Thank you.